Welcome to Zero Net Energy times 2 at cost, or the most abundant collector yet at cost. There are 5 necessary components to achieve a Zero Net Energy times 2 at cost. An envelope is thoroughly insulated, solid window coverings, a whole roof full of solar panels, a heat recovery ventilator in each room, and a hydronic air-to-water heat pump. Yeah, here is what we're looking at. You see the envelope is insulated. Do you see any leaks or anywhere or breaks? Not even any. Here's a R30 and R80 and R50. We're looking at this house from the west side. Here's the top, here's the south side, here's the ground. This can be what? This can be 1.5 stories tall. It can be 2.5 stories, 3.5 stories tall, but not 4.5 stories tall. The reason is we want the surface area of this envelope, which is actually a deep space radiator, because even though the heat inside is slowed down phenomenally, it still does get outside. So we want the usable floor space as large as possible compared to the amount of deep space radiator. Now this can be a home, it can be a church, it can be an office, it can be a government building, it can be a commercial space. Now this is a collector, this is a hot water collector with the glass moved out some. So those are black fins on tubes, and when the sun shines they get hot. These are the solar panels, and this is the hydronic floor. The solar panels here are contiguous, that is, they're touching each other. They look like the roof, and even though they touch, there's going to be some leaks over here, and so this is the real roof. This is the waterproof, and this we'll fix that up later. If you stand right here and look up, you'll see the back of the panels. Now this can heat the whole house. This can heat the whole house. If this breaks, this can do it. If this breaks, this can do it. If they both break, there's so much insulation here that, 7 candles at freezing, or 7 candles actually at 20 degrees can keep the house at 70 degrees all winter long. Now here, the wall is something like this. To achieve all that insulation, 2x4, 2x4, 2 feet apart, big windowsill. Here's the foundation, here's the slab, here's underground insulation. This is the structural, and this one is just resting on this slab. Coverings look something like this. Eight-inch chunk of foam, or equivalent, hung from the top with a hinge, center of gravity, teeter-totter, counterweight that pockets into the wall. Oh, happens to be 2 foot thick. There's room to counterweight that into there and still have a bunch of foam, enough to actually, if it's spray foam, it can equal R50, which this is anyway. So this moves up and down in a way that is perfect, because this hinge here is a special hinge. It's a plate on a plate on a plate with little knobs to turn it such that it aligns perfectly with the ceiling. It also aligns perfectly at each 4 corners and all the other angles, so it's always looks really attractive. Now here it overlaps for 9 inches, so it's an R50 here, R50 here, and that's practically an R50 here. When you walk into the room, the occupant sensor sees you and releases the catch, and because the counterweight is balanced to stay up by a few ounces, it swings open automatically and silently. When you leave the room, or upon some other settings, it closes really slow with a miniature motor there that will stop if anything gets in the way. Or, if all that breaks, you can do it by hand. Now, this is beautiful, okay? But look at, this is going to get in the way of the furniture. So, okay, over here, look at it, just clears. We'll have one big window covering. Over here in the stairwell also. Here there's a window right here. Well, the window covering is going to hit the couch, so that window has to be higher or something like that. That's the biggest problem. Now, here we have the sun coming in. It gets really hot, 30, 150, 60. The pump puts it into a big water tank. Now, when the sun starts going down, the pump, we'd like to keep this at 120, going in at, leaving at 120. So, if this goes down in temperature to 119, then we turn the pump off, because otherwise it would reverse and cool. This would then become a radiator and cool the tank off. Here we have the airflow going under here, through here. This is a heat pump. It's an air to water heat pump. It catches heat from the air coming through. Air, let's say, comes in at 40 degrees. It leaves at 39 degrees because this is run by electricity. It turns, there's a motor, it turns a compressor that does the refrigerant, that does its little magical thing, and collects and then compresses the Freon type substitutes. They don't use Freon anymore, and bumps this up to 140 degrees or more. The nice thing about this is it makes hot water without any carbons, because this heat pump actually collects heat that's already in air, amazingly enough, even in cold air. It uses 1/3 or 1/4 as much electricity compared to an electric hot water tank. All that's really good. Now, if we close off the attic space, plenum we call it, then it's going to get hot in the attic, because this is will absorb a lot of heat. The sun's shining, let's say the sun's shining, and of all the energy that comes from the sun, 20% gets whisked away as electricity. The other 80% turns to heat right there. Half goes this way and half goes this way. Well, we can collect that heat, and that what that does is it gives an advantage. Instead of 40 degree, it could be 50, 60, 70 degrees, so the heat pump doesn't have to lift as hard or work as hard, so it's much more efficient. It gives it a head start. Now, when we can, here's the solar day, let's say during the winter, we can increase the length of the solar day effectively by, that's over here, when this 119 is, or lower, it's still very good heat. So what we can do is we can take this too cold to put directly into there, and we can run it up to the heat pump, and it can bump it up further, and this then doesn't have to lift all the way from really cold. It has a head start again. Now, heat recovered ventilator in each room. Here's a cross section of the wall. Here's the outside, the inside. These are thermometers. It's cold outside. This is a thin aluminum plate. Gets hotter as this air channel, two separate air channels with a fan in each, because the hot air from the inside gives up its heat, because heat always goes to cold, and ends up, well, let's see, that's 90% efficient. So the air channels do not touch each other, but the heat does transfer. This thin aluminum plate is actually huge. Here's what they really look like. The outside air, and here's the core, the thin aluminum plate with a whole bunch of little channels, every other one. Then here's the fan to the inside. The inside then crosses this way and gives up its heat and to there and continues on out. Now, this is kind of neat because it actually fits in a 2-foot wall very handily. Now, what would happen if, well, these fans are really quiet. You can hardly, they move real slow. It's kind of, well, that's because you want the air to dilly-dally around here so as to change the heat over. But if we put these on a higher speed, they wouldn't dilly-dally so much there, and the efficiency would go down from 90 to maybe 50 or 30 if you really got going on those fans. So there's one of these in each major room. How do you turn them off and on? With a CO2 switch. So if he's in the room breathing, the CO2 switch detects that it needs some more fresh air. When you're gone all day and nobody's in the room, why have these things going? Even though they're very efficient, saves, because they're zoomed, they're zoned, yeah, they're zoomed. And so when you're in a room, they turn on, essentially, and when you're not there, well, they don't. So you only freshen up the air that you need, therefore they run about half the time compared to one of these in a whole house, mixing up all the air all together. There doesn't really work very good because, oh, well, the CO2, the carbon dioxide that he's breathing, we breathe, or from cooking with gas, if you had gas, or from burning the cars outside. Well, the outside is pretty darn fresh compared to the inside. The CO2 is very related to the VOCs, volatile organic chemicals, that are constantly emitting from all the rugs and the couches and the plastics and everything that, oh boy, and they're all mixed up, and there's 10,000 of them, and the EPA doesn't know what the heck they are. And so it's better just to flush those out, or better yet, to get rugs without any, but still there's always some. So it turns out that we don't need to measure the VOCs because the CO2 reading is very much related to the VOCs. So you don't have to worry about the VOCs, except if you were gone all day and the VOCs might have had a while to evaporate. You could then turn the heat recovery ventilator on high flush. So you, just for a few minutes, you'd flush out the room, and you'd have fresher air right away. This is way better to do than putting a big one of these in the old, which is really, really good for an existing home or building. But what that does is the VOCs in one room gets blown all over the whole, all the house air is mixed up, and so if something was burning in the kitchen, you'd smell it all over the house, whereas each room is its own cell this way, and it limits the VOCs much better. Now, here's the wall, the supporting 2x4, the resting 2x4, the foundation. These are the 2-inch thick foam, hard foam insulation. The slab, the 24 inches there allows enough so that we can put these 2x4 arrangements not staggered but in line, and they can be cross braced all you want, because the thermal shorts of 24 inches with wood at an R1, then that's the minimum then is an R24, which is fine, because actually all this is going to turn out to be about R70. So when you do the whole envelope, it's averaged, so we can endure that short at R24. Now this is actually a loose fill of any kind is just fine, and that R70 is the real R value, the measured, not what it says on the label. So when we go to assemble this thing, first of all we put up the whole frame, and then we put up this wallboard on this side. We come in and spray vapor barrier paint sloppily all over this area, and then we can maybe fill in some of the gaps with a seal, or if there was some cracks or something, we're going to check on that. The reason we want to have vapor barrier paint is that when you cook, when you breathe, it's what, a quart of water you breathe out every night or something, and when you cook and hot showers and everything, the moisture, when it's cold outside, it's a small molecule, goes like heck, and it just walks through every little, oh boy. And what happens is, normally without this, in most houses, it goes into the insulation, and let's see, it gets about this far, and then it starts getting really cold, and it condenses, turns to water, and it runs down and drips and rots the wood. And even in here, it's so moist, just like trying to stay warm with a wet blanket. So then we go ahead and put in the windows and seal up the heat recovery ventilators, and put in a blower door, and get the IR camera, the infrared camera that can see the heat really amazingly. And the blower door pressurizes the whole house, or vacuums it, and we can watch for the air, and the camera can just totally see it. The air, any leaks, oh, we missed a little spot there, and that's where we get a little sealant or some vapor barrier spray foam, yeah, foamy stuff, and that way we can verify right then and there the whole envelope is totally airtight and then vapor tight. Now, when we assemble this thing, we put up the sheathing here. We put this wallboard up first. That's all we have up so far. Then we put up the sheathing on its side, and then fill up the loose fill, and then another of the same. And then at the very top, way up there, there's going to be another thin 1 foot or something to finalize, so we can always top it off if we ever had to, which you can tell really easily with the IR camera. They'll be around forever. But properly done, you'll never have to top it off. Now, out here, there's a rain screen. I didn't show it. The shingles or whatever are kept off the outer sheath, plywood or whatever, by half an inch or an inch. So the air can dry this. So it doesn't really need any vapor barrier or anything over in this side, because we want that air, when the moisture in the rainy, really high humidity, it dries out, because it doesn't hardly get anywhere at all. It's such a small amount compared to what comes from the inside. So this thing really is in the right place, does the right thing. This could be insulated any old way you want to. This other inside wall board, so this is the run for all the water pipes and wires and whatever. Now, the let's see if I can find that. There we are. Back to the window coverings. Now, there's a soft foam right here, really, really soft, so it seals thoroughly. And since the hinge is so adjustable, it just, everything's just perfectly sealed here. So what happens is, when the window here eventually leaks, even with the good windows, the little wind blowing in, with without that, it gets this far, and the house just doesn't leak when it's windy or at nighttime and all the window coverings are closed. That's kind of nice. Now we could make these foldable right there, and they could accordion, let's see, they could go up like that, something. But that's complicated. It'd be nice, but it wouldn't hit the furniture because this would just essentially go all the way up. Or these can be pocketed into the wall. That'd be a lot more expensive and be a maintenance problem. So it's really, really better to stay to this simple design and arrange the furniture in the right place. Now, here is what we're really going to do. Let's see this one. Okay, insulation all over the place. Okay, this is a truss. This is all kind of structurally one. The truss goes way up into here. Okay, we've put this real roof there. Photovoltaic panels, more solar panels up here. And, oh, the pink should have, and the vapor barrier, I should have put that up all over. So the picture here required this to be brought in, so it can be way bigger going back. Since this is actually an R50 average, real-time insulation, when the sun comes in, oh, we lost that greenhouse, okay. When the sun comes into this window, and the sunbeams hit the floor and heat the thing up, well, it's going to get so hot, we don't even want the sunbeams. So this is not a passive home. This is not a passive structure. Passive has big windows here and no windows over there practically, or over in the sides either. Well, here you can have all the windows you want. Oops, cannot go down to the floor. Or you can, but you can have windows all the way around the house. And this way, it's really good light. It's wonderful to have big windows on the north side. Okay, so here we have our 2-foot wall. And let's say, okay, I don't want to do all those 5 necessary components. I want to do all this, but, we'll just skip this part here. Okay, so if you built this big expensive wall, 2 foot, did everything like this, but you didn't have these, the heat needs of the whole house would come down about 40%. Okay. Now, if you did just the thick window coverings on a regular skinny wall, thin wall, the heat needs would come down about 10%. Either way, the payback would be 60 years. So cost effective, not even. But if you do both, the window coverings and the 2-foot thick R50 wall, the heat needs go down to, wow, 4%? Yikes. So this is actually such a thoroughly insulated envelope, could call it a heat sealing envelope. So this works because the heat that you generate inside from this being and cooking and all normal average American activities will provide enough heat that it gets out to the envelope and can't get through these walls fast enough to get out all the way down to 32 degrees, almost freezing, or actually freezing. So in other words, your internally generated heat will heat the whole home all the way down to freezing without turning on the heater. So, oh, and if you have apartments with a whole row of condos or something, you don't have to turn on the heater until 0 degrees. That's 0 degrees, all the way down to 0, no heater at all, with average use. Now if you went on vacation or something and nothing was turned on, well then you have to turn on a little heater to keep the pipes from freezing. Now, at a regular home, 2,200 square foot average single family residence, when you get down to, we'll talk about that, 32 degrees, and below that you're going to have to turn on a little bit of heat, but it's only 1/5 of the amount of heat that you normally would have to turn on with a regular stick home. Now, that heat would be, let's see, well, we just light a candle, you know, it's okay, or turn on some extra light bulbs or the big screen TV, yeah, it'll work. Best way to do it is, though, that gets coefficient of operating performance. The heat pump is actually up here, and it would run down the hot water tank, would then feed the hydronic floor. But wait, that's a big radiator. That's just a radiator. There's already a radiator in each room. Oh, I didn't tell you that yet. That's because the heat pump, makes the hot water runs to each room in a radiator because the heat pump has a reversing switch and it is also an air conditioner. Well, you'd have to have an air conditioner when it's hot. So since there's already, well, it's kind of a modern looking radiator. What do we need this radiator for if we already have one? Okay, and since we need such a small amount of heat, rarely actually, we'll just use the radiator that's, they're usually about up here. And so, geez, we don't even need that. The hydronic floor. And geez, when it gets really, really cold outside and you have to turn on the heater, if there's sunbeams happening, yeah, that'd be fine then. So, let's go up to the attic up here. The roof, this is a real roof. It's nicer because it doesn't have a bunch of penetrations, although the existing homes with the solar panels roof mounted, those things are not leaking. So this is one big old structure, or any way you want to. And since there's no shingles under here, we don't have to re-shingle later on. It's easy to clean this, so there's a freeze-proof water outlet up here on a little hose. You gotta crawl up there and stand over here, and you can hose off the panels if you needed to. It actually doesn't happen very often, and unless you're in a dusty area. Oh, there might be a little leaf or something caught there. We can get that off and clean these and clean those. And this is a perfect rain catch, okay? And later on we're going to catch those a few drips there and get them out without dripping down here, so this can be a usable storage space. Looks better than roof-mounted solar. Sometimes looks kind of tacky, although they're okay if you do it right, if you arrange them right. Also, the wires are accessible, and so you can wire the voltages or segment off some, or maybe for different voltage of a car that's coming down, or different heat pumps or whatever. So you don't have to tear them all up. You can also check them to make sure they're working right. Also, the panels here sometimes get old, or what if one did break? Well, you have, okay, so you put the new one in there, and it sticks out like a sore thumb because it's not aged. Well, these over here are the same kind of panels. They're pre-antiqued. So you put the new one up here, put the old one, pre-antiqued, in there, and so it will look better for the longest time. Also, with this space up here, the heat pump is sitting right up top, so it can catch that heat. It's nice to have the heat pump out of the weather. Most of them are sitting beside the houses, right? That way the heat pump could last a lot longer, and it only works once in a while, so a few hours a day. See, it probably lasts pretty long time. Well, that's could really happen because it only works 4 hours a day average, which collects enough heat, because you don't need much, that's the trick, in the bucket for the whole night. Now that hydronic heat pump also does domestic hot water and any space heat that might be needed by the heater. So the heat pump works way less. And that daytime use, then it's not as cold in the daytime when it does work those 4 hours. Normally heat pumps run all through then when it is really cold, and they have to work really harder. So that efficiency is something like a added efficiency from the daytime bump up temperature advantage is something like 14%. The motor here in the heat pump is a 220 volt DC motor. That's what they're making these days. And the solar panels are arranged at 220 volts DC. So instead of going from DC to the house inverter, then over to here to this other inverter that they're putting in the heat pumps now, and the inverters do actually double AC, DC, DC, AC, and it's all together a DC, AC, DC. Every time it loses efficiency. So the direct connection from DC to DC causes the heat pump to run a 20% greater efficiency. Oh, and then we already had a 14%. And then there's another 5 or 10% because this plenum here, even though we're going to be pulling air through, still, when the sun's shining, it gets hotter. And so, what, 40% increase for the heat pump to make hot water, and without any extra cost. Now, because this air is being moved through here either by natural chimney effect or some extra fans here, keeps the panels really cooler than putting them right on the roof. In fact, for proportion, a 300 watt fan will pull enough air through there to increase the output of the solar panels by 10%, because the cooler you keep the solar panels, the more electricity they put out. So roof has the advantage of increasing. Okay, so if you had 20K on the roof, or on this part here, that's 2K extra that you get just by the placement. Also keeping the panels cooler, they do actually last longer. So that 2K, well, wait a minute. So when it's dim, okay, there's no heat anywhere, okay? So when it's cloudy for like a month at a time, like it does get in some places, a lot of places, the solar panel still continues to make electricity, about 1/7, let's say. So we have 3K all the time for like what, a short day, 8 hours or something. So we have 24 kilowatt hours to work with all day long, and that's without the grid. Of course, you always have the grid, so it's just fun to figure it without the grid. And because the heat pump works at such a high coefficient of operating performance, the DIM has plenty of electricity to run the heat pump directly. We're not going to the grid at all. Plenty enough to make enough hot water to run your domestics. Okay, if you got to be careful now. I'm not talking about the grid yet, just for the fun of it. No grid. Short showers, but enough to get, and it also makes enough electricity to cook and do a few things, not the big screen TV. And if you needed to add some extra heat. So if the grid went down, which it isn't really, come on, but if it did, well, this whole thing doesn't need the grid. And with a couple of extra, maybe just even one, car battery, too, would be better, all night long, and it's not going to make anything, huh? The batteries would be enough to run the heat recovery ventilators to bring in fresh air, if you turned everything off at night and didn't do anything except your computer or some little battery lights. So you don't need a big bathtub full of batteries yet. You can have that, but you just really don't need it. So this is a little bit taller. Normally this would want to go flatter, but it's taller because it's better dim collecting and better for collecting the heat underneath to give that bump up for the heat pump. Because altogether this 20K collects 40% more altogether energy per year. It's 40. So let's see. So that's what, that 20K ends up being 40% more efficient. Oh, now that it's going to snow. Some places it really snows. The snow's going to cake up on here, ice up. So what you can do is open the door here and let some of the house heat in, and that will melt that off. Maybe you could close that. You don't really need to. Or you could get a little propane heater in an emergency and heat this place up, and it would all slide off. Usually it slides off by itself, and there are coatings that they haven't started to use. This bed over here, you're going to have to get out there and shovel it. I don't know. And maybe make a little place to shovel it out over there. Get a snow blower, leave it there. Oh, the roof structure here is so super trussed that the snow load won't bother it. But the better solution for way north, Minnesota, etc., you can run this all the way up and make a peaked roof and get everything else done just the same, and it works fine. It's just that it's a taller, so this is nicer. So altogether, the most abundant collector yet at cost is the maximum efficiency possible on this little parcel of land, this little chunk of land right there. I don't know, I'm sure there is, but I can't find it. Some way to collect and use more energy than this can. The domestic hot water ends up being 2 times cheaper than any other way to make hot water. This is the most efficient at cost. Now, it's all integrated, okay? You need all these things in this location to get this thing to work. There's no experimenting. It's proven technology, the best off-the-shelf equipment. It's sturdy. Yeah, it's redundant. Like if it just works. I mean, everything broke, you can keep it all going with a couple of candles in each room. You'll be 77 degrees. Yeah. Boy, I hope that battery makes the heat recovery. You might have to open the window a little bit, but the heat recovery. Oh, there's one in each room. That means there's 5 of them. And the whole house runs on 2? So you actually have some spares if you opened all the bedroom doors or something. So no matter what is coming up, this can really handle it, whatever the future brings. And it might last, because the wood stays dry, it might last 200-300 years. It's the simplest, it's intuitive to operate, it's easy to upgrade because there's room in the walls and everywhere. If something else comes up in the future, it's easiest to fix. It's user-friendly. Can somebody beat this? I hope so. I can't find it though. So I call it the Zero Polluting Hummer SUV of Zero Net Energy homes. Now, legally, a Zero Net Energy home converts the annual solar radiation falling on its structure to produce an amount of energy equal to the energy consumed by the structure itself and by the occupants of the home while in the home or on the immediate surrounding property, all of which is utility net metered over the course of a year. And that includes full utility. That means with all the lights on, regular American use. We're not like wearing sweaters and at 60 degrees and reading with flashlights. The Zero Net Energy times 2, or most abundant collector yet at cost. This whole design was invented by starting with a solar panel that went all the way down to the ground, went way up high, big old triangle thing, and then putting a house underneath. Well, geez, we needed some windows over here, and the headroom wasn't right, and step by step by step over the years, now it's actually, well, it's a magnificent sun collector, a veritable solar-wide receiver manifesting aggressive energy-generating design at every turn, which happens to have a living space coddled underneath. In reality, each is integrated with the other, resulting in a total home output performance of 85% self-sufficiency in the winter and 290% in the summer, for a yearly average of 200%. Now, if we took a regular existing home and tried to get the same zero net per year, there'd be like 4 times as many solar panels needed. Okay, so if we took that, in reality, that existing home, we can put enough solar panels on the roof, average if you have sun and some, if you have some of the roof pointing the right way, to get 30% of the home's energy. That'd be really good. With solar panels. Also, if we go through and do energy retrofit or energy performance upgrade, that's where the energy performance contractor comes in with a camera and a blower door test and finds all the leaks and fixes the windows if you need a new window, and all the blower, you have to call it all the ductwork sealed up right, and everything, little thing that they can do. That's an up and coming, wonderful, huge industry, actually. So he can get 30%. In other words, you can reduce the energy bills in both ways by 30% each. So at 60% you could get optimum. It's an optimal average with the high-tech retrofitters that are coming right up. That won't do the car. So, and that's at cost. So you're going to pay it back, and it works out. In other words, it's funded by the energy savings. So if you borrow $30 a month to pay for the loan that is going to pay for the energy performance contractor and or the photovoltaic installer to do up a $30 a month energy savings each, so that'd be $60 a month. This is average. So you're paying the same amount of money, except you're paying less on your utility bills, but you have an extra check to pay in to the loan. Well, they are arranging it so it's all on bill financing with the utilities. So you probably have that. So the advantages of the most abundant collector yet at cost is that in a regular home, half the energy is for space heating and cooling. 15% of the energy is for making hot water, so altogether heating is 65%, which leaves the plug load, or the gizmos and outlets, only actually 1/3 of the total home need. Well, okay, here we've done all the hot water and all the heating all within itself. It doesn't need the grid. Well, when the sun is shining, then the sun can provide the gizmos. Well, at night it can't. So altogether, the gizmos are about half and half. So that 1/3, half of 1/3 is 1/6. So this design only needs the grid 1/6 of the time. Well, the grid really likes that. The grid is not really big enough for all the cars coming and people coming. So 5/6 of the energy is produced on-site and stored on-site for overnight. Well, actually, even though we use the whole solar panel for collecting heat, the actual electric part, we only need half of it for the home. The other half is for charging the car, about 30 miles a day, an electric car, regular size electric car. So that's really nice. So this does the house and the car net over the year at net zero. So, if you don't have an electric car, that other half here goes to the utility, and well, they buy it from you. They'd be more than glad to buy it from you, except if they don't need it, they'll let you know. That's kind of rare. And all these panels are at cost. Okay, this is at cost. The panels are separate. That financing is done by a third party, the standard in the United States today. So you don't pay for the panels. They just come in. Somebody else, it can be anybody, your neighbor, your banker, your utility, some Wall Street guy. Better to have a local group to actually own and collect the tax liability, and then you pay them the same amount as you normally would on your electric altogether. And after 15 years or so, then you've paid it off, and you can contract to buy it up for really, really cheap, and they work for 50, 60, 70 years or something. So this is not a vote for nuclear or coal or gas. Altogether, this over the lifespan is 1/15 of the pollution compared to a regular home run on fossils that will have to be restructured at some time to not, which is an extra step. Oh boy. And this is 1/10 of the carbons compared to a regular home. You still got to make it, and etc., make the panels, etc. So it's the cleanest machine we can do. And we need to teach how easy this is to assemble, because it's all the regular 2x4s. Kind of ain't nothing fancy like straw bale or compact earth, or oh boy, all kinds of things out there, tires or something. The theory, though, to understand is really pretty complicated. How all these gizmos and all the different modes of operation, how it all integrates, is really fun. But it's got a learning curve. These subjects are the same subjects that the energy performance contractor, which is very likely to come into your house and do an energy performance upgrade. That's a science that we need to get started on. And so this speaks exactly to the very same subjects that the energy performance contractors who do the energy performance upgrade to your home or business, which will be happening And so if you understand this, it's a lot more fun. So because this is, well, this is fun because there's no heater until it's freezing. Or if you have shared walls, there's no heater to turn on until it's 0. And that's at 77 degrees. Yeah, really, 77 degrees inside with fresh air. Okay, so in a single-family residence, at 32 degrees, no heater until colder than freezing, and then only 1/5. Okay, what happens if it's out here? It's not 32, it's 40 degrees. So this heat is not going to escape fast enough, so it's going to build up. So it's going to get hot. 40 degrees, it's going to get, geez, 83 degrees inside. That's too hot. Aha! So in the wall over here, the heat recovery ventilator, it knows by its thermostat to turn up higher to become less efficient to breathe in for you more fresh air. That's how it does it. So we're cooling the house at 40 degrees and increasing the amount of fresh air by a factor of 2. So to turn up the fans higher brings more fresh air for free. Now what happens if it gets to be 50 degrees outside? Okay, so what we're going to do, we'll reverse the fan going out, and we'll make both fans in the heat recovery ventilator blow in. So there's 0 heat recovery, but and so it does it perfectly and keep the house at 77 degrees just by reversing the fan. Now that's major fresh air. You're getting down to 600 parts per million right there, or even less. Well, now the legal most you're supposed to breathe is 1,000 parts per million of CO2. We're talking about CO2. So outside right now it's 400. You can get those little gizmos and measure it. They're like $100 right now. It's coming way down in price. Well, we want it to be as close to 400 as possible. Well, inside it just doesn't happen in most buildings. Right now you're sitting there breathing way more. I'll bet you. If you had one of those CO2 displays, it would show more right now where you're sitting, more than 1,000 parts per million, which ASHRAE says, hey, that's going to make you a little sleepy and suggestible and giddy and maybe even a little hungry. So this freshens the air. Oh, and then of course removes any VOCs that are hanging. 2 times, maybe 3 times, because what we can do as it gets hotter and hotter, we're going to have to cool it more, so we'll turn all these blowing in from the cool side, turn these going out, so it does a cross ventilation. Okay, it's getting hotter outside, hotter now, so that's still not keeping up. Well, somewhere along the line, I hope all these window coverings opened. Yeah, they did, actually. So if it's 70 degrees outside, and you're cooking and doing all this kinds of stuff in here, it's going to be too hot in here. So at that point, well, what if there was a whole house fan up there? Or, gee whiz, remember we have an air conditioner. Might have to turn the air conditioner on. If you're busy in here doing all kinds of cooking and showers, you'll have to turn on the air conditioner at 70 degrees. Oh, well, you could just open the doors or something if you did. Or the air conditioner. Oh, that's because the heat pump is also an air conditioner with its reversing switch. I think I said that. And the radiator is also, so there's another tank, or the same tank, actually. The heat pump fills up a cold water tank. Should fill that up at night in the summertime when it's cooler. Yeah, you don't have to. That'd be okay though. And then that has little tubes that go over to the radiator that fans out the cold air. So even though you were designed a long time ago at 250 parts per million CO2, and now you're breathing 400, it looks like we're all going to breathe 500 outside. So the atmosphere has doubled our design parameters. So we want to stay as close or down. Many rooms go up to 2, 3, 4,000 and you don't even notice it. You can get used to anything. So if this is such a hot design, why didn't somebody figure all this out sooner? A whole bunch of reasons. The major one is that the equipment, this thing, these are up to 20%. The heat pump, oh my goodness, they put the inverter on it. They have better compression and better refrigerants. The heat recovery ventilators are so much better. The fans are 60% more efficient than they were only 5 years ago. Better ECM fans. And now the CO2 switch, it turns it on at the wrong time, at the right time. That was $1,000 even a couple of years ago, and they're now down to $30 from the factory. And a bunch of other things that have really only come online in the last 1 year or 2 years. Also, this is talkable now because of global warming, and this doesn't make any carbons at all, or only a little bit, depending on what's in the grid, and you don't even need that. This actually works just fine without the grid. So, dollars-wise, this is an excellent investment because you're freezing in all your utilities at today's prices. Once you're buying your electricity at, say, I don't know, 11 cents, you're going to pay 11 cents for the next 30, 40, 50 years. And the grid prices are going to go up and up and up. Also, if the car is charged with this amount, at this price today, this is 2014. Let's see, that's about $1.50 a gallon equivalent altogether for an electric car. Well, 40 years from now, with these panels, you'll be paying $1.50 a gallon. So this is really, it's a cost positive for sure. When the mortgage is paid, well, okay, you have to borrow more money for all this extra stuff, but it equals a regular home plus utilities over 30 years. We'll use 30 years. So in 30 years here, you not only paid off your home, you've paid off your utilities also. So from 30 years on, there are no utility bills. Maintenance and everything else is equal. No, wait. Let's just wait. Okay. They're going to come along with some kind of super duper nuclear power plant that goes in your backyard, something, free energy device, whatever, in the future. So why should we do all this bother and put up with the window coverings, etc.? Because we hear about all these magical things gonna be. Well, actually, you really look into it deeply, there's nothing there. And even if there was, or I hope there is, this still is totally functional. So, and it's low tech, it really is. So, it won't be cheaper. It's not ever going to be cheaper. So it's better to do it now because the incentives and everything are good right now. So there are three kinds, you could say, there are three kinds of heaters in the world: gas, electric, and heat sealing envelope heater. So this is the basis, along with the symbiotic arrangement and placement of the gizmos and the components of the zero net energy times 2 at reality right now, or the most abundant collector yet at cost. Hey, pictures. I think there's some, let's see what we got here. I gotta put one of these together and pay for it and work out the details. And first one's gonna cost a little bit more. Yeah, I need a hand with that. But by the 10th or the 100th one, they'll be cheaper than a stick home. With utilities, you could just say, okay, when you buy a stick home, the builder has to include 30 years of utilities, which is doable. Well, then what happens after the 30 years? Here's the gist of a whole roof full of solar panels. Just lots of solar panels. Oh, here we go. We've got regular existing homes with solar panels added. And, oh, some in the fields there. That's nice. Only 30%. It's not going to get the cars. And we need more solar panels. And you can't collect the heat under them. Now this is kind of nice. Something like that, pretty close. One big flat roof. And now here's the shared walls. This is my favorite. No heater needed until 0 degrees. Cheaper, better. Oh boy. This can not do the cars though, because there's so many smaller units. Well, this could be one big condo for a rich person. Yeah. 0 net energy times 2 at cost.